Precalc, chapter 7.6. Guys, this first part, super easy. We're talking about complex numbers again. So complex numbers, you guys should remember, complex number is a plus bi. We have that in the middle of all of this. A plus bi, that's a complex number. What we have to realize is that we are going to have to graph these. And when we graph these, we are going to use a two-dimensional graph now, instead of just a one-dimensional. It's not just a number line. And so we have a real part and we have an imaginary part to this, because complex numbers, remember, are made up of an imaginary part and a real part. So A stands for the real part. BI is the imaginary. Did I say it wrong? A is the real. BI is the imaginary. So B is the number we'll use on the y-axis. So we have a real axis, we have an imaginary axis, and when you go to graph that, it looks like our normal XY. But we call it our AB axes. And that together makes up the complex plane. You guys should have done that possibly in Algebra 2. Last year, Geotrig, you guys probably graphed complex numbers. We're going to do it again today. Really easy. So basically, you can think of it as the point A comma B, X comma Y. So when I go to graph Z, now Z, guys, is what we call a complex number. So Z1, the first complex number, is 2 plus 3i, which means what? 2, 3, or 2 to the right and 3 up. Boom. There you go. That's our complex number Z1. Z2, 1, 2, 3, down 2, and it's there, not that other thing. So there we go. Easy enough. I gave you a homework assignment with 100 of those. You guys are quite happy. But then they start to do things like Z1 plus Z2. And how do we do Z1 plus Z2? Isn't Z1 just 2 plus 3i plus 3 minus 2i? Can't I just get rid of the parentheses and gather like terms?
Nope.
Yep. Add the real parts together, add the imaginary parts together. So this becomes 5 plus I. 1, 2, 3, 4, 5, 1. Boom. There you go. Easy enough. We're happy. Ready to move on. So, the next logical step, guys, in this is not just to graph a point, it's to graph a set of complex numbers. So, here we go. Remember how these things work. We got some brackets here. It's saying that S is a complex number of the form A plus BI. That's what it's saying. S of A plus BI. So we got a complex number with us. There's a line after this. It's a little hard to see. It's such that where A is greater than or equal to 0. Wait a minute. What is that symbol? Greater than or equal to. That is called an inequality. What do we know about inequalities? Bless you. What do we know about inequalities, guys? There's shading going on. They're shady, right? It's kind of like Jake the Jake. Shady. That just made the video there, buddy. Okay. Now, if that means there's shading going on. But guys, in the problem of A plus BI, A acts like what letter?
X.
X. So the only restriction to your complex number is that A, or X, has to be greater than or equal to 0.
Oh,
Can you graph that?
I think.
Here's our axes. I'll change colors. A equals 0. Whoops, not dotted though, is it? Solid line. And where is A greater than 0? To the
Right.
It's all numbers, complex numbers, that fall into this area. So, is that a solution?
Yep.
Is this a solution?
No.
No, because it's not in the solution set. Pretty simple, huh? Graph the second one. Still talking about complex numbers, A plus BI. a has to be less than 1. So it's a vertical line that's dotted, shaded to the
Right.
left, because it says less than.
Oh, yeah.
And
Left.
we have a b is greater than or equal to 0, so there it's a solid line at y equals 0, shading up. So we would say that our solution set is basically the second quadrant with a little bit of a sidestep into the first quadrant. Now, some more information. I see that it got cut off there. So this is supposed to be the modulus. So the modulus, aka the absolute value of a complex number. So we're calling z complex number that is a plus bi. So if I take the absolute value of z, it actually becomes the absolute value of a plus bi, which is the square root of a squared plus b squared. Hey, that's Pythagorean's theorem. But why is that true? Wait a minute, guys. What does it mean to be absolute value again? What's the definition of absolute value? All positive, but why is it always positive? Because it's the distance from 0, and distance is always positive. Complex numbers are the same way. If I have a complex number that's out here at a plus bi, would you not agree that that would be the distance to the center or to the origin? That line. But guess what, guys? That line forms a right triangle with the x-axis when I drop straight down, right? And that means this side is A and B because I move A to the right and B up. So if that's true, if A and B are my sides, then isn't it natural that the hypotenuse is the square root of a squared plus b squared? Which is the absolute value of z, the distance from the origin to your point. Okay? Now, later on, in the next slide, we would also call that r for the radius of a circle. And you're going to see in the problems here that's going to start coming up. Guys, so if I wanted to, part A there is calculating the modulus. Yeah, the moduli for multiple. That's true. No, it's moduli. Okay. Would you guys agree that it's just the square root of 3 squared plus 4 squared, which is square root of 25, which is 5. Hey, that's a special one triangle anyways. That's a 3, 4, 5 triangle. Some of these get really easy that way. Others are not. The next one is the square root of 8 squared plus a negative 5 squared. So, 64 plus 25 square root, which equals square root of 89, and then you would simplify that if you can. Pretty easy enough, I would think. Again, but then all of a sudden now below, it wants you to graph a modulus. So now they're saying, hey, if I have you say that C is a complex number, it's in the complex plane, that's why it says Z, but it has the restriction such that, that's a little line, the modulus, the absolute value of Z, is equal to 1. Well, how do I state that, or how do I figure that out? Wouldn't you guys agree that the modulus, again, is that a squared plus b squared with the square root would equal 1, right? What happens if I square both sides? I'd get rid of the square root.
That'd be a squared plus b squared equals 1 squared, or 1. That looks really, wait a minute, wait. That really looks close to something. What did a kind of represent on our graph? X. B was, isn't that x squared plus y? It's a circle. X squared plus y squared equals 1. It's a circle with a radius of 1. So if I went to go graph this, boom. That's a little, actually larger than 1, I guess, but it's a circle. It's all the values on that circle would make that true. Pretty cool, huh? I think so. Part B, which says D is the real numbers such that the absolute value of Z or the modulus of Z is less than or equal to 1. In this case, guys, it's actually asking us for the circle, right? It's still a circle with a radius of 1, but it's an inequality, so we have to shade. Are you shading in or are you shading out? It is in. How do I know that? So it's the exact same picture here. How do we know where to shade? We check your point, plug something in. What do you want to put in? Because think about this, guys. It's where is a squared plus b squared square root less than or equal to 1? Well, isn't there a nice little point right there at the origin? When is 0 squared plus 0 squared, oops, not parentheses, square root, does that make that true? And if it makes it true, then you would shade it in. I use the same drawing for both of those. I hope that's okay. So, last year you guys learned this as SIS Form. They don't write it as SIS Form. They keep it expanded. They called this the trigonometric form of a complex number. So, I had to put that paragraph in there, or those couple sentences, because it kind of explains why or everything works out. So, you still have Z being your complex number, which is a plus bi. We're going to do here is we are going to graph that point out in the open, and we are going to form a triangle with the x-axis and the origin. So if I had a plus bi, everybody's okay with this. We just got done graphing these, where a is your side, b is your other side. And what they're going to do now is say that the modulus, the absolute value, the distance from your point to the origin, we're calling that r. And I think you guys have done this before. So we would call that r. And then the angle that's formed at the origin and this x-axis we call theta. Basically, guys, I know you guys have all done this because you guys should remember this. 260 degrees. Polar coordinates. SIS form. It's all the same, guys. So, you keep going around and around and around, right? 4 different answers sometimes for the same coordinates. Okay. Here we go, guys. R is the absolute value of Z, or the modulus. A squared plus B squared, take the square root. That makes sense if you got a right triangle. I didn't write the right triangle in there. Well, we have a right triangle. Does everybody agree with this? We just did this anyways. So we agree that R can be the square root of A squared plus B squared. Also, if I construct this triangle the way you see it, if I ask you, what is the cosine of theta? What's the cosine of theta? Cosine theta would be A over R. If I wanted to get A by itself, I would just multiply by R, right? So here's A, which we have stated up here. So do you guys agree that A would equal R cosine theta? Just rearranging things using SOHCAHTOA. Can I do the same thing with sine? Sine would be b over r. So I'd multiply both sides by b, and therefore sine, or b would equal r sine theta. So sine theta is equal to b over r, multiply both sides by r. So that's b. Well, isn't a complex number a plus bi? So therefore, a plus bi would equal r cosine, not a, but cosine theta, plus I sine, or r, ir sine theta. I took out a and b and put in their trig functions. Can you see that? Notice that I put I in front of all of this mess. And I did that on purpose because we don't want to get I mixed up with being inside the trig function. We also should recognize that R is in both of those. So I am going to take R out, or factor it out. And I get cosine theta plus I sine theta. Last year we would have called that SIS. Okay? All of that, guys, summed up right here. I have that as listed. And so then I also put this box in here. Complex numbers of the form a plus bi have a trig form. We just created it. R times cosine theta plus I sine theta, where R is the modulus. And the tangent of theta will have the same ratio of b over a. That makes sense because here's theta. Tangent is opposite over adjacent. Makes sense? So our job then is to take a couple problems and convert them from standard, complex standard form to trig form. Here are the problems we like to do. I only did the first two with the other class because it's just repeating itself over and over. The first two end up being reference triangles, so it helps us out a little bit with identifying or kind of seeing the connection. But here we go. I'm going to try doing this, give you guys a little work time without me giving you much information other than graph it, find r, find theta, and then put it into the formula. Try that on your own first. Okay, so the first thing I'm going to do is graph the problem. Going over 1, up 1, there you are. Okay, so we have this triangle with sides 1, 1. We have r, and we have theta. Now that I got this graphed, I got my sides labeled. I have r and theta labeled because r and theta are the key to this whole process. R is not too bad. To find r, it's 1 squared plus 1 squared. Take the square root, which ends up being the square root of 2. Actually, hopefully, all of us would have recognized that's 1, 1, square root of 2. That's a reference triangle. That means when I go to find theta, theta should be really easy too. What's theta? 45, we'll call it pi over 4. Right? So that's easy enough. But what happens if this wasn't one of my reference triangles, didn't recognize this? How do I find theta? Well, the key is use tangent. Because tangent of theta is opposite over adjacent. That's 1 over 1. So you can use your unit circle. When is tangent of theta equal to 1? It's 45 or pi over 4. Or take the inverse tangent. Inverse tangent. Inverse tangent. You get theta equals pi over 4. So now we know theta. We know r. Write down the formula. Z equals r sine, not sine, but cosine theta plus I sine theta, and fill it in. Square root of 2 cosine pi over 4 plus I sine pi over 4, and you're done.
That's it? That's all we can do?
Now, the question that came up first hour was, will I ever have to go back the other way? And the answer is, sure. You guys know the cosine of pi over 4?
Yeah.
Square root of 2 over 2. What's the sine of pi over 4?
Square root of 2 over 2.
And can you distribute the square root of 2 in?
Yeah.
And if you do that, you end up with 1 plus 1i.
Whoa!
It's easy enough.
So
So,
that's, we can't go any farther than that?
that's as far as you'd go. That's what I'm asking you to do. Part B, guys, same thing. Now you're going back 1, up square root of 3, right? So it's square root of 3, it's negative 1. Using Pythagorean's theorem, what's square root of 3 squared plus negative 1 squared, square root 2. There's theta. Theta would be what? If you don't know, just say theta is equal to the inverse tangent of square root of 3 over 1. Oh, wait a minute, Mr. Konchak, that's a negative 1. Why didn't you use negative 1? We were kind of confused first hour with this. People didn't want to accept the fact that the angle in quadrant 2 that we are finding is a what kind of angle? Has a name. Starts with an R. Reference. All reference angles are positive. So I could care less because of ratios being positive or negative. I'm looking for the root angle, right? The angle that will give me that specific square root of 3 over 1. And so therefore, I'm just going to choose positive ratios because everything will be referenced to the first quadrant, which is positive. I will deal with it with signs being positive and negative by all students take calculus later. So what do you get when you put inverse tangent of pi over 3? Or what angle is associated with square root of 3, sorry? Inverse tangent of square root of 3 would give us an angle of 60 or pi over 3. So that means the angle in here is pi over 3. So when I go to use my angle, or my switching to my forms, the answer is 2 parentheses cosine of, no, not pi over 3. It's 2 pi over 3. What? Why is that, guys? Because you're in second quadrant. You now have to actually know the fact that that was a reference angle to the larger angle to get there. You guys kind of seeing how those, you're going to take the spin. Just like yesterday, that problem in the last board where I said, if I did 2, 120, I would spin 120 first and then walk out 2. You remember doing that? That's what we're doing here. We're turning 2 pi over 3, then walking 2 forward. Polar form. Homework, guys, I'm keeping it simple. I'm doing 3 problems like these and 1 graphing problem. So 15, 44 through 46. Have a great day.